Hey everybody. Hi Tristan. Hi Ian.
Hey there.
Hey, thanks for being flexible on this. I know it's kind of a last minute change to go virtual here, but yeah, I was just feeling a little bit sick over the weekend, and I didn't want the first day of school to be like, I exposed you guys all to COVID. So I appreciate you guys being flexible.
That's probably a good idea.
Share my screen.
Can you hear me all right, by the way?
Yeah. I can hear you just fine.
Cool. I wasn't in school during all the COVID stuff, so I'm not used to the Zoom classroom.
Oh, it's different. It's weird. Um, do you have any other classes that are virtual this semester?
Yours is my only class this semester.
Okay. Yeah, hopefully we're not virtual for too long. And so I'm still waiting for my test results, but yeah, hopefully we get back into the classroom pretty soon. Actually, we'll be right back. I'm gonna grab some water. Hi, everybody. Welcome. Yeah, thank you guys for being flexible today. It's I know it was a kind of a last minute change to go virtual, but but yeah, I've just been feeling a little bit sick over the weekend, so I didn't want to have the first day of school be me exposing you guys to COVID. So yeah, I appreciate you guys being flexible. Hey, Alex, how was your summer? Mm. Oh, I bet. Yeah, it was good. Yeah, actually, I spent a lot of the summer kind of working, kind of slowly getting back into kind of doing stuff normally, but also still being kind of cautious too. So yeah, it was good. I learned a lot about ANSYS this summer, so I'm ready to share with you guys this in this class. Um, so the school really doesn't want to go fully remote again. Um, and actually, off the record a little bit, I might be a little bit in trouble for doing this, for kind of changing to virtual like this, but they really don't want to. But I think um, they might have to. But with them requiring vaccinations and everything, I think they're not really seriously considering going full remote again. But well, of course, we'll have to see how things go. Yeah. Question. Will this course be in person, or will the lectures be recorded in class and be done at home? So the plan is to have this course be completely in person. And so that's the plan, but things might change as well. And so depending how things go, we'll see. But the plan is to have this in person. Yeah. We have one of the nice computer labs in CS 309 that have a really nice version of ANSYS on them, and so we want to make use of that. Who chose which classes went online and in person? That is a great question. And so for certain classes, like the required classes, I know that the department basically just defined which ones should be in person or not. For classes like this, which is like a graduate or elective course, which is there aren't that many not that many instructors that could teach this. We were able to put some preference in there, and so I put some preference to have this one in person. Just because last semester with the finite element course, it was really hard to do it virtually, just because I felt like it was really hard for me to kind of help people debug issues, and so I requested this one to be in person for that. Yeah. Will you need ANSYS downloaded on your personal computer? So since we're going to have access to the computer labs, you don't have to, but it can help, and especially if you want to work on stuff at home. Yeah, so there's a free version that you can download, but the one inside the computer lab is much nicer, and those computers are pretty nice too. Yeah. Yeah. All right, it's 5:30, so let's go ahead and get started today. All right, so welcome everybody. Welcome to the fall semester. Welcome to EGME 540. Okay, and so the title for this class is Computer Applications in Engineering Design, which is a generic as fuck title for a class like this. And so honestly, they gave me a lot of freedom for what I could do with this class. And so I did kind of something that I thought was really cool, that had something to do with computers, that had something to do with design. And so, that's kind of, my thing with that, okay? And so first of all, let me say that, thank you guys for being flexible with this. I know that this class was planned to be in person, but I was feeling a little bit sick over the weekend. And so I didn't want the first day of class to be, me exposing you guys all to COVID and me sending an apologetic email afterwards. And so, I thought, let's just have it virtual. It's just the first day anyway. And so, let's just kind of be safe and be cautious with this, okay? Because it is, this is a really important semester for this, for our college. So, we want to make sure that, we keep you guys as safe as possible, right? But if you're just kind of tuning in just now, this class is planned to be completely in person, and part of the reason for that is because of the large software aspect of this. Okay, and so this, and I know maybe some of you guys might be there right now, but but this class we have one of the nicer computer labs in the CS building for this, and so it'd be really nice to use those computers so you don't have to kind of download this really heavy program on your personal machine. And generally, it's a lot easier for me to kind of help debug you when it's in person too. Okay. All right, quick question. So can we take this class without having taken EGME 410? Yes, absolutely you can. And actually, especially if you're a graduate student, I would prefer that you take this class without 410, because actually, we're going to be building up a lot of this stuff from scratch. Right? And so, kind of a peek behind the curtain, we're kind of looking to get rid of some prereqs like this, where 410 it's not a required class even for our undergrads, and so it's a little bit awkward to have that as a prereq for a graduate course like this. And so and so what we're trying to do is we're trying to make our graduate courses a little bit more self-contained, and so you absolutely shouldn't take 410 before this. Okay? But if you have taken it, it's totally fine. We're going to be coming with a different perspective, right? Especially for I saw that there's several of you who were in 410 in the spring, and so actually I think this class will be really interesting for you too, because we're going to look at it from a very different a different perspective than what we did in the spring. Okay. All right, and so today, my goal is, we're just going to introduce the class, and so we're just going to talk about what the class is in general, and then we're going to talk about the syllabus, okay? And so we're not going to be doing any kind of ANSYS stuff today, and so it's just going to be, just kind of introducing just the course in general, right? Because I always find that, whenever I come to something new, whether it be like a new book that I'm reading, not that I read that many books, but or maybe I'm watching a new movie, right? It really helps a lot to really kind of get a sense for, what can I expect from this experience, right? Because if you go into just for as an example, like if you go into a movie and you expect to, for it to be an action movie, but then it's actually like a horror movie. You're going to be a little bit thrown off, right? And so I think not enough of university courses do this, where they kind of prime you for what to expect from the semester. And so I want to kind of spend today doing that, so that especially with the title of a class, where like this title can mean anything: computer applications and engineering design. And so there's a lot of different ways that we can take this course. And so I want to make sure that that you guys leave this class today knowing what can I expect from this class. And and if this class is not for you, then that's totally fine too. And then I think you can kind of make that decision after today. Okay. All right. And so today's the first lecture. My name's Professor Justin Tran, and here we go. Okay, so a little bit about myself. Oh,
Professor,
question?
I just have a quick question. So what if one of us gets COVID? Are you gonna like simulcast at that point, like, make accommodations to simulcast the lectures, or like on Zoom and in person at this, just point the camera at the whiteboard or something, or the computer, whatever you're using?
Yeah.
How are you gonna do that?
Yeah. No, it's a good question. So I think I think the policy that the school has of it is that if one of you guys test positive for COVID, or if you're feeling sick, definitely stay home for that. Unfortunately, the classroom doesn't have the best setup in the world for doing kind of simulcast, where they because like the webcam, there's no real good spot for it in the classroom where you can get a good look at the whiteboard. And so, I will turn it on, and so I will have it point at the lecture, just if just at the very least, just so that you can kind of hear what I'm saying. But unfortunately, we don't have the best setup where you can kind of see the board. I think that the fortunate thing about this class is that we're going to be working with the software a lot, and so even when we are in the classroom, a lot of times I'm just going to have ANSYS on the screen, and so I think that'll be a lot easier to stream. And so yes, and so I'll try to I'll try to be I'll try to do everything I can to make sure that the stuff, all the content in the class is available both in person and also via Zoom as well. Yeah. Okay. And so a little bit about myself. And so so my office is in the CS building, and so I'm on the 5th floor up there. So CS 526. Okay. My email is very easy to remember. It's called justran@fullerton.edu. Okay. And so if you just think of, I just ran a 5K, or just ran, a marathon, that's kind of what you should remember from my email, right? And so I grew up around here. And so I grew up in Cypress, California. And so if you don't know where that is, that's just, 8 miles west of where Fullerton is. It's just south of Cerritos. Okay. And so I did all my schooling in California. So I did my bachelor's at UCLA, did my master's at UCSD, my PhD from Stanford, all of which is in mechanical engineering. Okay. And my research interests lie in cardiovascular stuff. And so I like to do, see how we can apply engineering tools to studying heart and blood disease. Okay. And one of those tools that I use a lot is finite element analysis. And so this class, it's pretty near and dear to my heart, because it's one of those engineering tools that you can apply to lots of different things, especially biomedical stuff. Okay. And I'm also interested in STEM education. So, what are more effective ways that we can teach these classes that, you guys feel like you learn as much as possible and you feel good about your education. Okay. And so let's talk learning objectives. And so I'd like to have these at the beginning of every single class. And so if you had me before, you've probably seen these a lot. But if you haven't had me before, what you'll notice is that I like to put these at the beginning of every single lecture, right? And so you can kind of think of these learning objectives as kind of like check boxes for what you can expect for that day. Okay. And I write these learning objectives kind of very intentionally to kind of start with the verb. Okay. And I do that so that it'll describe to you basically what you should be able to do after the lecture's done. Okay. And so just as an example today, right? So after today's lecture, you should be able to describe the use and utility of finite elements in engineering work. Okay. And so after today's lecture, you should be able to, get on the phone with your mom or something like that, or get on the phone with your best friend and say like, hey, this is how finite elements can be used in engineering work. Okay. And so I write these learning objectives to kind of, almost seem like tasks that you guys can do after the lecture. Okay. And so what I always recommend to people is that, when you come into the lecture, write down these learning objectives, and then, after the lecture is done, look back on them and say, can I do this thing after today's lecture? And if the answer is yes, then that's great. You got what I wanted you to get out of this lecture. But if not, maybe you should review the notes a bit more, maybe talk to me, and we can work through that stuff. Okay. And so for today, we have a learning objective to describe the use and utility of finite elements in engineering work. We're also going to learn about the steps towards running a finite element simulation. And we're also going to go over the syllabus. And so we're going to prepare for the semester by understanding course objectives or course expectations and policies. Okay, and so let's jump right into it. And so what is finite element analysis and why is it important, right? And so finite element analysis, it's a numerical technique for solving differential equations on arbitrary geometries, okay? And so at its core, I've underlined numerical there on purpose, right? And so what that means is that, finite elements basically takes a physical problem and formulates it in such a way that we can use computers to solve the problem, okay? Because computers are, I like to call them kind of the smartest dumb thing in existence, because computers can be really, really powerful, but they're at its core, it's only really powerful at doing kind of the simplest stuff, right? And so in terms of kind of engineering analysis, what you can think about is computers are really, really good at performing arithmetic and algebra at really, really high speeds, okay? But if it's not arithmetic or algebra, a computer will be like, I have no idea what to do with this, right? And so finite element analysis, what the point of that is to kind of take a very complex kind of physical problem, a very complex engineering situation, and put it in terms of a arithmetic or algebra problem that a computer can do. Okay, we're not really going to be getting into the specifics of how that happens. If you are interested in the theory behind that, you can take a EGME either 410 or 541. But this class, we're going to be focusing much more on just the applications. Okay. And so what does this mean for the engineer? And so for the engineer, what this basically means that, with finite element analysis, they'll be able to predict how a physical system will react when it's subjected to external forces, okay? And so a lot of times, as an engineer, you're going to be designing systems that are, going to be interacting with the outside world, right? You're going to be designing a building that's going to be subjected to wind force that people are going to step on, that's going to be subjected to gravity, right? You're going to be designing a fin, or a thermal system that's going to be subjected to heating, right? Or maybe you're designing like a fluid system that's going to be subjected to a certain amount of flow, right? And a lot of times as an engineer, you're interested in saying, is my system going to perform well, or is it going to break? Is it going to, completely fall apart, right? And usually you want to find these things out before you actually build it, right? And what finite element analysis allows you to do is to find out that stuff before you actually build it, right? And so it's, it's very quickly becoming a very essential part of the engineering process, and a very marketable skill that you can use to go out and find a job, right? And the nice thing about finite elements is that it's not really limited to, complexities in the geometry or the loading of the boundary conditions, right? And so a lot of times, when you're doing kind of hand calculations, you're limited to kind of really simple situations that it's just so that you can actually solve the problem. But finite elements aren't really, limited by these things. And so, and the nice thing about that is, most engineering systems are, in this category where they are, they have a complex geometry, they have complex loading that they, that you need to solve for, right? And so finite elements kind of really gives you a chance to really analyze these systems in detail. Okay. All right, so let's talk about the different kinds of analysis that are out there. Okay. And so when you're performing what I like to call an engineering analysis, a lot of times you're trying to find out some information about your system, right? And so let's say that you have a car, right? And you want to find out, whether this car can withstand, an impact. Let's say it's crashing into a tree, right? And so there's different ways that you can go about finding out that information, right? And so the first way that you can find this out is with, what I like to call analytical methods, right? And so these are pen and paper calculations that solve, essentially you're solving some governing equations, you're doing some math, but because you're doing the calculations by hand, they have to be very, very simple, right? Because there's, even the humans with the highest computing capabilities, there's no way that they can do, computations on the order of a computers, right? And so if you're doing analytical methods, a lot of times you're doing simple kind of calculations. Kind of, I think the term that people use for this is called back of the envelope calculations. Okay. And so, analytical methods are great, and so they have a role. And so, it's not that people don't do these in industry, but they are limited to simple problems or simple calculations. Okay. All right. And so the second type of analysis out there is experimental. Okay. And so the idea with experimental is that, if you want to find something out about a physical system, why don't we just actually try it out on the physical system, right? And so if you want to find out if your car can survive a crash into a tree, just crash your car into a tree and see what happens, right? And so that's called running an experiment, right? And so this is great because, any data that you get from a physical experiment is kind of the best data that you can get. And so a lot of people call it like the gold standard of data, right? And so if you crash your car into a tree and it completely crumbles, right? No one's going to argue with that because they can see that the car is messed up, right? No one's going to, say that like, oh, I crashed my car into a tree. Oh, you're fake news, right? No one's going to say that because they can see that your car is fucked up, right? Right. And so experimental methods is kind of the best way to get, reliable data that everyone can agree on, and you can handle complex situations, right? As if you can build it, you can run an experiment on it. But the downside with experimental methods is, it's very costly, it's very time consuming, right? And so if you want to find out if your car can survive crashing into a tree, maybe there's a better way of doing it than wrecking your car and having to buy a new one or pay for the repairs, right? And so, it goes like that for engineering companies too. Okay. And so the third type of analysis, and the one that we'll focus on mostly in this class, is called computational. Okay. And so in terms of how it solves a problem, it's kind of similar to analytical in that we're solving governing equations, right? And so we're doing math, but instead of doing it by hand, we're having the computers do the calculations for us, right? And so the benefit for that is that, we can handle these very complex situations since the computer can do calculations that far surpass human capabilities, right? And so, it's a great tool, right? But the downside to computational methods is that it takes a fair bit of training in order to use it correctly, because and as people can attest to that have taken finite elements before, there's a lot of ways that you can mess up finite elements, right? And it really takes some good training to make sure that you set it up properly and you really know the software and you really get results that you can actually believe, right? Because if you run a simulation, and you go out into the workplace and you do finite elements, I think the primary challenge that you'll find is that, especially from older engineers, from more senior people, is that they're not going to believe what you did. They're like, oh, you messed up something. Oh, I don't believe these results or something like that, right? And so people are going to argue with your computational results, right? And so kind of a big part of this class is going to be, how do you set up your simulations? How do you, set things up so that, you can actually attest, you can defend the reliability of your simulations. Okay? All right. Any questions on this so far? Okay. All right. So let's go over some examples, right? And so one example that I like to show is like a analysis on a beam. Okay. And so this is a problem that you've probably seen in a previous class, right? So a lot of times, and so here we have a beam. It's subjected to some kind of distributed loading. And oftentimes you're interested in, what's the deflection in this beam? What's the stress in this beam? Okay. And if you have just a very simple beam like this, it's relatively easy to do. Like we can just solve the beam equations. We have just a simple 1D beam. It's good. It's all good in the hood, right? But if you want to do kind of a more complex beam analysis, let's say that you want to find the stresses of all the beams that come at this junction right here in this really massive building, that's going to be a lot harder to do with hand calculations, right? And so you're going to have to rely on simulations to do this kind of thing for you. And your results are going to look something like this, where you have kind of this color contour of, this probably is it looks like the stress distribution in this beam. Okay. All right, so let's do an example from heat transfer. Right? And so if you want to find out, what's the temperature distribution, or how the temperature varies in a solid block of material like this, it's simple to do if you have just a simple situation like this, right? But if you want to find out, what's the temperature distribution in a turbine, as it's running, as hot air is running past it, or hot gas, that's going to be a lot harder to do when you have with just hand calculations. And so something like this, you're going to have to run a simulation in order to get, the information that it's going to be useful for you. Okay. And then lastly, we're not going to really do much of that in this class, but you can also do fluid flow simulations. Okay. And so if you have fluid flow in a pipe, you can, and you have a simple situation like this, it's not too difficult to solve the equations and, find out what the velocity looks like. But if you want to do something more interesting where, let's say that you want to solve for the velocity of blood or velocity of fluid in your blood vessels, right? Then you would have to run a simulation on this because the boundary conditions, the geometries are much more complex. Okay. All right, and so let's brainstorm here. And so I like to turn this to you guys, especially for a graduate class like this. I think a lot of you guys are coming in with a lot of experience, either if you're working in industry right now, or from your undergraduate experience or stuff like that. And so what are some situations that you may have come across in your work that you think, or maybe you come across from a previous project that you think you can apply finite elements to, in order to analyze it.
I can jump in here, Professor.
Yeah, go for it.
So a lot of the experiences I've had with finite element analysis. So I guess just to give a little background, there's something that a lot of electronics companies will use called a brazed cold wall heat exchanger. And typically it's a really thin piece of metal with a empty volume on the inside, and there's some sort of intricate path, for those of you who might not be familiar, where the fluid flows through. There might be some fins on the inside, just bent pieces of aluminum that are bent hundreds of times in a really small space. So they'll use finite element analysis to kind of develop a model of what kind of pressure drop they could expect throughout that heat exchanger, and also at the same time they'll use it to determine what sort of heat exchanger capacity they have available over the surface area of the brazed cold wall. So it's kind of a twofold process where they'll use CFD to determine exactly how the fluids functioning on the inside of the device, and then also what sort of cooling capacity it could provide to electronics that are mounted to it.
Yeah, no, that's awesome. I think that's a perfect example, because it's like you have so many things going on in there too. Like you have the fluid flow, right? Like you have to determine the pressure drop, which if you have a complicated geometry like that, it's not trivial to do. Like you would have to find simulations for that. And just by nature of being a heat exchanger, of course you're interested in how much thermal load it can offload from the device, right? And actually, that reminds me, like I remember talking to someone, like a heat transfer faculty, and he said, the thing with electronics and computers right now is it's, the limiting factor right now isn't that we don't know how to produce more powerful chips. Like we can produce more powerful chips. The problem is cooling. And so the problem is, how can we offload, the heat from these chips so that they don't melt themselves, right? And so, heat transfer actually has a lot more to do with electronics than I think most people realize. Right? One video that I remember is, I think AMD kind of broke the record for flops or something like that, and they had to use liquid nitrogen to cool their devices, and it was kind of an amazing thing. But yeah, thank you for sharing. That's I think a perfect example of what finite elements can do, and what and how they can contribute to an engineering project like that. Yeah. Anyone else have anyone else have something they've seen in their work before, or maybe something that you guys are interested in learning for this class?
Yeah, I was gonna bring up that we can do FEA on nitinol, certain stents, and what their radial force is on the actual vessels at different vessel sizes and circumferences. Something that is kind of involved in my work right now, and so it's something that I'm actually interested in researching.
Yeah, absolutely. Yeah, thanks, Michael, for sharing that. That's a great application too. And Michael was actually in my bio was a cardiovascular class in the spring too. So definitely we talked a lot about stents back then too.
Yep.
So yeah, absolutely, finite elements is a great application for that, because the thing with stents and anything with any kind of bio application is that, you know, the geometries are often very, very complex, and they're not kind of a simple thing. And so a lot of times you need finite elements to really, you know, understand kind of, you know, or get the data that you really need from that, because otherwise it would be impossible. Yeah. Yeah. Thanks for sharing. All right, anyone else?
Hey.
Hey.
Yeah. Can you hear me all right?
Yeah. Yeah. Mm-hmm.
Cool. Yeah. So at my work, we make pressure regulators for zone 3 of like aircraft engines. So it's like the hottest part of the aircraft engine. So pretty much we use FEA to simulate the flow through small orifices in the regulator so that we can choose like orifice diameters so that we can achieve the pressure necessary to make the valve regulate, because it's a fully pneumatic valve, no electronics. So yeah, just another.
Nice.
Yeah.
Nice. No, yeah, yeah. Thanks for sharing. Yeah, those kinds of devices are really, you know, because I assume it's compressible flow that's coming through there, right? And so there's that adds kind of another layer of complexity too. And so, you know, whenever you have a gas or something flowing through these devices, any kind of complex geometries, like you need kind of finite elements in order to do that. Yeah. Right. Yeah. So thank you everyone for sharing. So I feel a little bit bad because you guys shared, you know, such great examples that involve like fluids and thermal and stuff like that. But I will say that for this class, you know, we're going to focus mostly on structural mechanics, just because I think it's a little bit more natural to kind of think of those things. But you know, a lot of what we're going to learn in this class, you know, a lot of like on the meshing and how to set up the boundary conditions. A lot of those things can be applied to, you know, thermal and fluid simulations too. Yeah. And actually too, excuse me. You know, I know a lot of you guys are coming in from 410, and so you know, you might be having some deja vu because these slides are very similar to the slides I presented last year too. And so you might be wondering, you know, what's different about this class compared to 410. And so, you know, what I did this summer is I got this book. You know, it's a book that I have for this class too. And I learned a lot about ANSYS. And so I would say back in the spring, I was an ANSYS novice. And so now I'm an ANSYS advanced person, right? And so I know a lot more about ANSYS than I did before. So I'm really excited to share that with you guys. And so, you know, I think, you know, probably what you guys see is that the class might start out a little bit similar to how we did, you know, last semester for 410. But as the semester goes along, you know, we're going to get into a lot of really advanced features in ANSYS. You know, I have 3 new activities planned for this class. I'm going to modify a lot of the old activities, and we're going to be learning a lot of, you know, really just kind of learning finite elements from kind of a practical standpoint instead of a theoretical standpoint. So I think, you know, I'm really hoping that you guys enjoy this class because I'm really excited for this class. Yeah. All right. Okay, and so now let's kind of move on to the next thing. And so next I want to talk about, you know, kind of the general steps to performing a finite element simulation. Okay, and these are, and you know, these steps that I've listed here, you know, these are the kind of the steps that you would go through, you know, as if you were, you know, a professional engineer using one of these softwares and you know, what are the steps that you would use to actually run your simulation within these softwares? Okay, and so I have 3 here, and so I think these are 3 of the more popular ones. They're not the only ones out there, but you know, of course, we have ANSYS, which is the one we're going to use in this class. We have Abacus, which is another popular one. That's one that's more popular in the academic community. And another one that's actually rising in popularity is SolidWorks simulation, right? And so, you know, I don't know, I know some of you I've had before, but, you know, I know that in the past I've kind of shit on SolidWorks simulation before, mostly just because I didn't really understand it. But I think it can actually be reliable for some things. So, you know, I know Dr. Myral kind of likes to shit on SolidWorks simulation sometimes too, but I think a lot of it just comes from, you know, we don't really understand it all that much. Yeah. But you know, I will say that I don't really understand it yet, but you know, I am willing to learn more about it before I can I can shit on it with a more qualified opinion. I'll say that. Yeah. Oh, I see. Yeah, and so I will say this, and so a lot of companies they might use, I think a lot of companies do use SolidWorks simulation just from a cost perspective, right? And so if your company is using SolidWorks already, they're probably paying thousands of dollars for the licenses, right? And if they want to use ANSYS in their company too, that's another several $1,000s that they have to pay for the license too. And so it's really convenient to have a finite element software in SolidWorks. Just because it's all there. You just have to pay once. Yeah. Okay, and so the steps that we're going to go over is first thing you have to do is you have to define your geometry. Then you have to specify your material properties. Then you have a mesh, boundary conditions, solve, and then analyze results. And so we'll go over kind of what all of these means. Yeah. Yeah, so every company kind of has their own software that they like, and as Khan was saying that it's really convenient when it's all in one software. So if you can CAD, if you can simulate, if you can produce drawings all from one software, that's super convenient. All right, so the first step to any kind of practical finite element simulations, you have to define the geometry. Okay, and so what that means is that you have to define what the thing is you want to run your simulation on, right? And so most of the time, this comes in the form of some kind of CAD file, right? And so, I think, most of us here are familiar with CAD. And so CAD is just it just stands for computer aided design. And all it is just kind of a digital representation of the geometry that you want to simulate, right? And so here I have a couple, examples of CAD files. And so on the top here, you can see we have a bridge, okay? And you can see that, this bridge is it exists inside the computer, and so this is not a photo, right? There's no such bridge that's on top of like a waxed showroom floor that you can see the reflection so nicely in there, right? And so this is a computer rendering, right? And so this is always the starting point for when you want to run a finite element simulation, because that you have to define what you want to find out information for. Okay. And so the main thing is with this is that, we need to be able to have things where we can apply boundary conditions and constraints to, okay? All right, and so here I have a couple examples here that kind of correlate with these two pictures, right? And so let's say that if you want to find out, if the goal of your engineering analysis is that you want to find out the structural stresses inside a bridge, then you need a CAD model of that bridge that defines that bridge geometry, okay? And so another example is that, let's say that you want to find out how much this beam is going to deflect or how much it's going to deform. Then you need to have a CAD model for that beam, okay? And so a lot of finite element software actually has its own tools for creating geometries, right? And so actually ANSYS does have its own CAD tools in it, but I will say it's not as convenient and it's not as robust as like a dedicated CAD software like SolidWorks, okay? And so a lot of times what you'll find is that a lot of times you'll produce the CAD in a different software. So let's say that you'll produce your CAD file in SolidWorks, and then if you want to perform a finite element simulation on it, then you'll import the CAD file from SolidWorks into ANSYS. Okay. But a lot of these softwares they're trying to be they're trying to become like a complete suite of tools, and so maybe your company just has ANSYS, or maybe your company just has SolidWorks, right? And so, there might be less and less of this as, as these softwares kind of become more well-rounded. Okay. All right. And so the next thing that you have to specify is the material properties, right? And so now that you have your geometry, you have to specify what your geometry is made out of. Okay. And so, this is really important because different materials have different structural characteristics or thermal characteristics too, right? And so it's important to assign these properly to ensure that our finite element simulation will be accurate and reliable, right? And so if your bridge is going to be made of steel, right, you don't want to assign its material as copper inside your simulation, right? Because copper has very different behavior and very different properties than steel, okay? Or even plastic. Plastic would be kind of the worst thing, right? Because a lot of these materials, they have things like density, they have things like Young's modulus, they have Poisson's ratio, or if you're talking thermal, they have like thermal conductivity, thermal capacity, things like that. A lot of these properties have a huge influence on how that structure or how that geometry is going to respond to external forces, right? And so you want to make sure that you assign these material properties properly, okay? And so material properties, it might seem like a simple thing because, a lot of times when people think of like, structural material properties, they think of like elastic modulus, think of density, think of Poisson's ratio, right? They think of, yeah, it's, just a few numbers. But materials can become really, really complex, right? And so we'll go over this a lot later on this semester, how to assign these properly. But you can have, really complex materials like anisotropic materials, composite materials, non-linear materials, right? And so, for those kinds of materials, you need to be really careful about how you assign the material properties, okay? One example that's used a lot in engineering is wood, right? So wood is not an isotropic material. It's not a simple material, right? Because the thing with wood is that you have these grains, or you have these fibers that run through the wood, right? And the direction of those fibers has a big impact on the strength of that wood, okay? And so if you're running a finite element simulation on a structure that involves wood, you need to make sure you take that into account. Otherwise, you're gonna get basically garbage results, right? And so, material properties, I think, is something that people kind of gloss over. They don't really think about a lot when thinking of finite elements, but it's one of the most important things. And we're going to spend a fair bit of time, on, how do we quantify these things and how do we assign them properly within ANSYS. All right, meshing. And so I think this is probably, what we're going to spend the most time on in this semester, right? And so meshing is kind of the I think kind of the most iconic step for a lot of finite elements, right? And so when I say meshing, what that means is that, we're taking a geometry and we're breaking it up into a lot of simple shapes, right? And so it's a little bit hard to see from this image here on the top, but what we have there is like a CAD geometry of some kind of hinge or some kind of bracket, right? And so after it's meshed, you can see that, we've taken that bracket and we've broken it up into a bunch of simpler shapes, right? You can almost say that we've kind of pixelated, or we placed a grid on top of our geometry, okay? And so this is really important because, the way the finite element method works is that it takes your complicated geometry and it takes the complicated equations that you want to solve on these, and it produces a very simple algebraic system that the computer can solve, right? And so in order to do that, it needs to do this on a bunch of simple shapes, okay? Because underneath the hood, or what your ultimate goal is that, you want to solve these partial differential equations on your geometry, right? And the computer can't do that on this, complicated thing, and so it needs to break it up into a bunch of simple shapes, okay? And a lot of times these shapes have predefined choices, right? And so some popular choices are triangles, quadrilaterals, tetrahedrons, which is a four-sided pyramid, or hexahedron, which is a six-sided. Okay, that's a typo. It's not a six-sided pyramid. It's a six-sided box, right? And so it's six-sided pyramid would be kind of a weird thing, right? Right. And so, meshing is probably the most difficult thing in finite elements. And a lot of times, this is where you're going to spend most of your hours, performing your finite element analysis is, how do I get a good mesh on this thing? Okay. And it's really important because if you have a crappy mesh, then you're going to have crappy solutions, right? And so this is I think the thing that people struggle the most with, right? And so I'll tell you right here, and if you've done finite elements, you can probably agree with me here on the left. This is a shit mesh right here, right? This is a really shitty mesh just because it's really coarse and it's not really capturing the geometry well, right? But whereas on the right here, this is a really nice mesh because it's really detailed. All the elements are roughly the same size and whatnot, right? And so, throughout this class, we'll learn how first of all, how do we differentiate between a bad mesh and a good mesh, and then what tools are available in ANSYS, to help us get a good mesh like this, okay? Right. And one analogy that I like to talk about early on in terms of meshing is to think about your understanding of digital image resolution, right? And so, typically when you think of a digital image, the more pixels that you have, the higher quality your photo is going to be, right? And so same thing with the mesh. And so with the mesh, you generally want to have a good density or a good amount of shapes or a good amount of elements, in order to get an accurate result. Okay. And so generally what you can expect is that the more elements that you have, the better your finite element simulation is going to be. But we'll talk about this in a lot more in detail as the semester goes on. But we're going to spend a lot of time on mesh. All right, so any questions on this so far? Okay. All right, and so the next step is boundary conditions. Okay. And so with boundary conditions, what our goal with boundary conditions is to define, how our solution is going to act on the boundaries of our geometry. Okay. And so, the terms that we'll use a lot. So boundary conditions is kind of the general term for these kinds of things. But in this class, the way that we'll usually talk about them are in terms of loads and constraints. Okay. And so a load is any kind of external force that you're placing onto the structure, and a constraint is just some kind of way to kind of constrain the motion of the system, right? And so if we go back to our bridge example, right? And so for a bridge, an example load for that could be like the wind, right? And so the wind that's going to be pushing onto the bridge, it's going to cause some forces on the bridge, right? Another example of a load could be like all the cars that are driving over the bridge, right? And so the weight of those cars are going to place a force in the bridge, okay? The constraints for that are basically the places where we fix the bridge to the ground to basically prevent it from moving, right? So everywhere where the bridge is bolted into the ground or bolted into a structure, right? Those are going to be the constraints of our system, right? So all of these kinds of things fall under the general category of boundary conditions, okay? Right. And so, boundary conditions is kind of the other place, it kind of forms a triplet. And so, we've talked about material properties, we've talked about meshing. And so boundary conditions is kind of, the third kind of thing that you kind of have to be really careful of when you do finite elements. But I would say that boundary conditions are kind of challenging from a conceptual point of view, okay? Because a lot of times, you have a, if you want to perform finite element simulations, you're doing it on a very complex or complicated physical system, right? And so how to take that physical system and say, what are the right boundary conditions to apply on this? That's usually not an easy thing, because a lot of times you have a very complex situation on your hand, right? If we go back to kind of an example we talked about earlier, right? And so we talked about kind of the heat exchanger that Tristan was talking about before, right? And so, you have to have thermal boundary conditions on that heat exchanger, right? And so do you put a convection boundary condition? Do you put a radiation boundary condition? Do you put, a temperature boundary condition, heat flux, right? What you put there or any kind of combination of boundary conditions, it's not trivial. And then you have to kind of think about it a lot in order to make sure that you assign it correctly. And just like everything else here, right? If you assign the boundary conditions incorrectly, you're going to get, garbage results, right? And so this is something that you have to do, really carefully. And it's another thing that we're going to spend a fair bit of time on this class as well. Okay. Okay. And so now that we've assigned the material properties, we've meshed, and we've applied the boundary conditions, actually all the hard part's done. So your job as the engineer is done. And so now you're kind of like, I've done with the problem, computer take the wheel, right? And so now it's the computer's turn to kind of do their work, okay? And so what you'll see in ANSYS is that there's kind of a magical button called solve, right? And so when you click that button, you actually are kind of done. And so this is, at that point, you kind of wait for the computer to kind of do its work, okay? But underneath the hood or underneath the inside your computer, what your computer is doing is millions or even billions of arithmetic calculations in order to solve your finite element simulation, okay? And the way that it looks like is it looks something like this, where you have kind of a very large matrix set of equations, right? And so you might have, it's the way finite elements is designed is to create kind of a linear system, AX equal B, right? Where your matrix A is some kind of ginormous system like this, right? And even something like this doesn't even do it justice. And so, here you can actually see the individual entries, right? That's usually not the case with finite elements. With finite elements, a lot of times, you're talking about a matrix that's like millions by millions. And so it's something that's way too big, right? And so, I'm not kidding when, I'm saying that this is like millions or billions of calculations, because it's intense. But the nice thing is you don't have to do any of it. You can just, tell the computer to do it, and then it'll do it. It might take a while, but it'll do it for you. Right? But for larger problems, this is the part where you have to be a little bit careful, because if you have a relatively small simulation where you have maybe around 10,000 elements, you can do that on your desktop computers. But I've seen some finite element simulations that have over 100 million elements, and these you have to run these on some kind of supercomputer. Otherwise you'd be waiting your entire lifetime for the results to finish. Right? But for everything in this class, you'll be able to do it on your desktop computer, or in worst case, on the lab computers inside the classroom. All right. And so once the computer solves your results, then you can just then you're ready to look at them, right? And so the last step in the finite element analysis is to analyze your results, okay? And the way that these results are displayed are in spatial distributions of your quantities of interest, right? And so you're going to see a lot of figures like this on the right, where you have like it looks like a heat map of certain quantities in your structure, okay? And so this heat map will show things as like, what's the displacement in your structure, or what's the structural stress, right? Or they'll use certain colors to show you, where are areas of either high stress or high deflection, or blue to show where areas are low, low stress or low deflection, okay? Right. Another thing you can do is you can further process these results to show you things like where the maximum stress is and where it occurs, right? And this information can be used to predict whether a part will fail or not, okay? And you can do additional post-processing to find other quantities of interest. And I do want to cover a little bit more post-processing, because I think it's something that's not addressed a lot in these kinds of courses, but that'll probably come kind of near the end of the course. Okay. Okay. So any questions so far on the finite element process? Okay. All right. And so let's talk about finite elements and design, because this class, the title of the class has design in it, right? And so it's important to see, how does finite elements factor into design, okay? So due to the digital nature of finite element software, it's having a much bigger role in the engineering design process, right? And so just like we talked about before, simulations can really significantly reduce the need for physical testing, thus saving you a lot of time and a lot of money. Okay, but it's important to note, and this is coming from someone who really believes in computations and really believes in simulations, that it's never going to eliminate physical testing, right? And so at the end of the day, you should never just take a simulation at its word, right? You should never just say, I ran the simulations on this, I'm ready to build this part and to sell it to millions of people, right? You should never do that. And so you should always do some kind of physical testing, because no matter how good you are at setting up simulations, there will almost always be some factors that you don't account for, right? Sometimes these factors are fairly minor and they don't have a big impact on the results, but sometimes they can be really major as well, right? And so sometimes, you're not going to know unless you try it out, right? You can run all the simulations in the world about telling me that your car is going to survive crashing into a tree, but I'm not going to believe it until you actually crash your car into a tree, right? And that's coming from someone who who lives and breathes simulations for all of my professional work, right? And so I want to make that really clear, so that simulations could be a great tool, but it's never going to fully replace physical testing, okay? Right, but where it can really come in handy is making these kind of incremental modifications to your design, right? Because a lot of times the way that we design things is we kind of make one small change and we want to see how that happens, right? And if you try doing this with the physical prototypes, it's going to take you a really long time to design that part. But with a digital platform like this, you can make a design change. So like let me make this hole a little bit bigger. Let me make this part a little bit longer, right? You can do that, and you can use finite elements to know immediately what are the effects of that on the design, okay? And for any kind of industry where you're working with really expensive parts, so like either like aerospace is kind of the big one, finite elements is a necessity, because you're not going to be building tons of airplanes or tons of rocket ships to test your hypotheses. Okay. All right. And so another important point I want to make is that FEA is just a tool. Okay. And so it's honestly no better than the hammer that you use in your workspace, or the drills that you use, or or the rulers, or any kind of measuring, right? And so it might seem like a very sophisticated and very trustworthy tool, but it's just like any tool. It's important not to misuse it. Okay. And I think this is a really tempting thing for people that are getting to FEA for the first time, is that it's really tempting to run a simulation and think, oh my God, that looks beautiful. I think that's gospel. That's the truth, right? And so I want you guys to kind of caution against that, because it's really easy to set up an FEA simulation incorrectly and get garbage results, and then to trust that that's reality, right? And that's what happens a lot for people getting into this for the first time. Okay. And so in fact we have a saying for this in the simulation community called garbage in, garbage out, right? And so if you put garbage into your simulation, you have a crappy mesh, you assign it the wrong material properties, your boundary conditions are sus, right? You're going to get garbage out. And so you're going to get results that either don't make sense or just not useful to you at all. Okay. And so, FEA, it's a really great tool, but it's just a tool, right? And so, I want you guys to always kind of remember that it's you can misuse it, and people do. People misuse it all the time. Okay. All right. And so here's kind of the outline for what I have planned for the class, right? And so I have kind of 5 different phases of the class, right? And so in the first phase, we're going to go over what I like to call foundational knowledge, right? And so we're going to review some key concepts from mechanics, right? And then we're also going to do just a really, really brief background of theory and FEA, right? And so we're just going to fly through it. But again, if you're interested in more of the theory behind finite elements, there's a class for that. That's going to be EGME 541. Okay. And so the next phase of the class is, we're going to go over finite element basics, right? And so we're going to go over the 3 kind of key steps that I talked about in the process before. So we're going to go over material properties, meshing, and boundary condition, okay? And so, we'll get, I call this the basics because, we'll go over kind of the basics of, what you need to kind of get started on this. But it's we're going to leave a lot of the advanced topics and nuance for later, okay? Then we're going to have an entire phase on just meshing, right? So meshing is I think probably the most important thing to learn for finite elements, and we're going to learn lots of different element types in ANSYS, right? We're going to go into when you use certain element types, how do you when do you use them, right? And we're going to look into mesh metrics, how do you determine what's a good mesh or not? We're going to go into advanced meshing in ANSYS, so a lot of the advanced meshing features are there, okay? Right. And so after that, we're going to go into phase 4, where phase 4 is going to be a lot of the advanced topics and features in ANSYS. And so these are a lot of kind of the specialized analysis types that you can do. And so things like buckling, things like optimization, things like modal analysis, vibration, how to incorporate in design, okay, and advanced post-processing, okay. Non-linearities too, and so that's kind of it's a little bit of a mishmash. I will admit it's kind of a lot of the features that I kind of pulled from different places, but I think they're all really interesting and really useful for professional engineering work. Okay, and then phase 5, we're going to go over something important called verification and validation, which are tools that you can use to basically assess how reliable your finite elements are going to be, and that's a really important topic that we'll have to learn too. Okay. All right, so any questions on this? Okay. All right, and so I'm going to skip this slide just because we're not going to be covering background information that much, and we are running a little bit short on time, and I want to make sure I go over the syllabus. But background information is important, but we're not going to cover a lot of it. Okay, and so let's jump into the syllabus. And so normally at this point in the class, I like to pass out the syllabus so that we can all look at it. But unfortunately, we're on Zoom right now, and so you can follow along with the syllabus which is posted on the course website. Okay. All right, so let's talk COVID procedures first, because it's this class is planned to be in person. I know we're not there right now, but eventually we will go back. Okay. But since COVID is still very much a real thing, it's not going away. We want to make sure that we want to make sure that the health and safety of everyone in the class takes first priority. Okay. And so these rules, I have kind of these 4 rules right here to kind of help minimize the chance of spread while we're inside the classroom. Okay. And so number 1 is social distancing. Okay. And so, we're a little bit lucky in this classroom. CS309 is I think the biggest computer lab that we have in the CS building. And so I think this won't be too difficult. I think naturally the computers themselves are fairly distant apart. But, with that said, it would help me a lot if you guys, would kind of help with this as well by choosing where you want to sit. Okay. And so when you enter the classroom, try to choose a seat that's as far away from people as possible, right? And so, even if you're coming in with your friend, try to make it so that there's one workstation in between you guys, so that you guys aren't sitting next to each other. Okay. And we should be able to do that, with the size of the class that we have, and the amount of students that are in the class. And so we shouldn't have too big an issue with that. But there might be some people that have to sit next to each other, but try to spread out as much as possible. Okay. So when you're inside the classroom, a face covering is required, and so your face covering has to cover both your nose and your mouth at all times. Okay. And so it's been a long pandemic, but and so you guys probably know what the purpose of face coverings are. But the face covering, it has less to do with protecting you from particles in the air, more as preventing your particles from getting into the air, right? And so naturally, as we talk or as we cough or as we breathe or as we do all the other weird stuff we do with our mouth, like stuff comes out of our mouth, right, whether we know it or not. And so the face covering is there to kind of catch that stuff before it gets out into the air, right? And so that's kind of the purpose of that. And so I'll be wearing a mask at all times in the classroom, so all my weird mouth stuff doesn't get on you guys, right? And then I want everyone else to wear a mask as well. Okay. Can we model those particles in the class? If we were doing CFD, we could, but we're not going to be doing that much CFD in this class, and so we can't. But Dr. Myral and I, we have discussed developing a CFD class, and so that might be something that we do in the future. Yeah. All right, and so if you do have to cough or sneeze, I know everyone's going to be wearing a mask, but it would. But when you cough or you sneeze, a lot of stuff comes out of your mouth, and so it would help a lot if you cough into your elbow or you cough into a tissue, or you cover your mouth additionally to kind of catch more of those particles, right? And another nice thing is that the school is going to be providing us with cleaning materials, and so I'll be doing this too. And so if you have to run right after class, I know some of you guys have some other engagements, so no worries if you can't do this, but it would really help me out a lot if you could clean your desk and your chair, both before and after the class, right? I think this is especially going to be true for us because we're going to be working in a computer lab, and so you're going to be touching the mouse, you're going to be touching the keyboard, right? And so if you kind of wipe all this stuff down, it would help me a lot, right? And so if you use kind of the same policies that you use at the gym, right? And so after you use, usually after you use like a workout machine, you usually like to wipe it down, right? And so nobody likes, sweaty McGee, like, using the bench press and then leaving his puddle of, nasty ass sweat on the bench, right? And so, in the gym, we appreciate when people wipe stuff down. In the classroom here, we're going to basically use the same policy, okay? All right, so any questions on the COVID procedures? Okay. All right, office hours. And so here are my office hours for the week. And so my office is located in CS, and so it's the 5th floor of the CS building. And these are my times, okay? And so whenever I do office hours, I always try to spread them out, and so that that one of these times should hopefully work for somebody. But I know that that's never possible, and so it's always impossible to kind of match up with everyone's schedule. And so even though these are the times where I'll be definitely available for student questions, if you can't make it to these times, or if you want to talk outside these times, definitely shoot me an email, and I'm always happy to meet outside of these. Okay. And so office hours are always great for discussing any kinds of confusion you have with the course content. Whether it be homework assignments, exam questions. We don't have exams in this class, but maybe for the projects. But if you just want to stop by and just say hi or just chat, I'm always down for that too. Okay. And so I'll be having office hours in person, but I'll also have a virtual component to my office hours as well. Okay, because I think this is a nice thing, because it's a lot of times it's a bit tough, like especially if you're not going to be on campus at that time, or if you have other things or you need to be at home. I think it's nice to also have the virtual component too. And so I'll also be on Zoom during these times as well. And so if you want to sign on Zoom and talk to me from there, you can do that as well. And you can find the links to all these Zoom calls from the course website. Okay. All right, and so course level learning objectives. And so I also have learning objectives for throughout this entire course, right? And so these are kind of the goals that I have that I want to accomplish by the end of the course. Okay? And so these, I kind of think of these as kind of, I used to say North Star, but I freaking hate that term now because President Virgie uses it like every other word, and so I don't want to say North Star anymore. But these kind of like our guiding lights for the class. Okay, and so I kind of designed all the content for this class with these kinds of with these kind of learning objectives in mind, right? And so basically what I want you guys to get from this class, if I can sum it up in a nutshell, is I want you guys to leave this class, and if you can take a job at a company as a finite element engineer, you should be able to contribute day one you know, with just the stuff that you learned in this class, right? And that's my goal. And so, you know, we're going to be dealing a lot with the software. You know, we're going to be dealing a lot with kind of the practical considerations, practical applications. And so, you know, you should be able to take what you learned here, plug it into a company. You know, maybe you have to learn a new software, maybe you have to learn SolidWorks or Abacus, but a lot of the concept that you learned from this class can be directly applied there. Okay, that's my ultimate goal for this class. Okay. All right, let's talk assignments. Okay. And so there will be no exams for this class. And so I forgot to change the title of this slide. Okay, but there's going to be 8 assignments. Okay. And so each of those assignments is going to be an ANSYS, kind of an ANSYS activity. That's what I call them is. Okay. And so each of those activities are going to teach you basically, you know, either a new feature of the software or you know, or a different aspect of it. Okay. There's going to be one midterm project. And so that's going to be a project that's going to be due midway through the semester, and one final project. Okay. I haven't decided what the details of these projects are going to be. But I think with the nature of this class and, you know, because we're going to be working so closely with the software, I didn't think exams were going to be appropriate for these. And so, you know, it's going to be strictly just a project-based class. Okay. The lowest homework grade will be dropped, but please do them all. Okay. So each of these ANSYS activities is, you know, they're going to teach you an important aspect of the software. So even though I'm going to drop the lowest one, you know, please do them all. Okay. And so the reason I dropped the lowest assignment is because, you know, because I know, you know, throughout a 15 weeks or 16-week semester, like shit happens, right? And so, you know, it's hard a lot of times to keep up to date with, you know, all the deadlines, all the assignments all the time, right? Especially when you have work or you have other classes and just all the other just COVID craziness going on, right? And so, you know, I want to be flexible. And so that's why I dropped the lowest homework. But you know, if you can, you know, if you can't make a deadline for one of the assignments, please still do try to complete it, because, you know, I designed those assignments to, you know, to give you kind of the essential skills. This bullet point is a typo, which is what I get for trying to be lazy and copy and paste my slides. But there's obviously no midterm exams, and so there's not going to be cumulative or not. Okay. All right, question. So will the homeworks be done in class, or can we access the lab to work on them after the lectures? And so, yeah, it's a good question. And so I'll be giving you plenty of time to do the activities in class. But a lot of times I think, you know, you're going to have to work on it at home too, because I think there's not enough time. So you can either access the lab after hours. And so I think the lab should be open for you to do that. Or you can access it virtually. And so there's going to be a virtual computing lab that we'll go over next class. Which you can access, you know, remotely on the lab computers, and so that's an option. Or a third option is you can download ANSYS to your personal computer, which is the student version, and you can use that for your projects as well. Yeah, and so I will say that the student version that you download from the website is not going to be as nice as the lab ones, and so you might not be able to do everything that you can do in the lab ones, but the student one should be sufficient to do all the activities. Another question, are the projects individual or they group? They're going to be individual projects. Yes. Are those dates for the midterm and final pretty set in stone? So they are. So I am planning, you know, that these are going to be the due dates for the projects. But I do like to be flexible too. So sometimes I do like to push these back, you know, in case, you know, you guys are really busy during that week or something. And so I am flexible with these, but these are what I'm planning to do. Right? The only one that I'm not flexible on is the final report, because this is literally the week after finals week. And so, you know, they only give me until Friday of this week to finish grading, which is Christmas. And so, you know, I'd like to have Christmas with my family. And so, you know, I can't really push this back anymore, because, you know, I need to have time to grade this project as well as all the other projects for all my other classes. And so this is the only one that's kind of non-negotiable. Question, so which version of ANSYS will be used? So I think in the computer labs, I think they were just recently upgraded to 2021, but you can use 2020 for this, because we're not going to be using, honestly, it's you know, the new version of ANSYS, it's kind of one of those things where it's just an excuse to sell you the software again, but not that much really changes in between the versions. And so you can use 2020 or you can use 2021. Yeah, so both of them should work fine for this class, but the ones that are inside the lab itself should be 2021. All right, course grades. And so this is how the grades are going to break down. And so the homework assignments, those are going to be 20% of your grade. The midterm project's going to be 35%, and the final project is going to be 45%. Okay. And then from there, once all the grades are in and you have your overall course, course score, I'm going to assign you a letter based on your score. Okay. And so this is, I think, a fairly standard breakdown. Okay. And so, I use these as kind of a starting point, but I also like to be flexible on these, on stuff. So, I do take things into consideration. Whereas, if you turn in every assignment, or if you were there at every lecture, I tend to be a bit more lenient on that too. So, and so I do a little bit of adjustment at the end of the semester for certain students, but these are kind of my starting point. Okay, but there are limitations. Like don't come to me at like an 80. Don't come to me at like an 86% and ask me to bump you up to an A-. Okay. And so there's always like 4 or 5 students that ask me to do that every semester. And so I try to be reasonable. I try to be lenient, but there's limitations. Okay. All right. Any questions on this so far?
Professor, I have a quick question.
Yep. What's up?
Do you have any tips for doing well in your classes?
Yeah, it's a good question. So usually what I say is, just keep up with the homeworks, ask questions, and keep up with that. But that's usually for an exam-based class. So this is, and so I'll be honest. So this is the first time I'm doing a strictly project-based class, and so I've never really done this before. And so usually when I assign projects for these for my classes, I tell students to start as soon as possible, because I think kind of the trap that a lot of people fall into is that they look at a project and they say, okay, I think I need about 4 hours for this, 3 hours for this, and then I'm good. And then they start literally 7 hours before the project is due. But the thing with projects is that things happen throughout the project, and you're going to struggle with things that you're not going to expect you're going to struggle with, and you need to give yourself the time to kind of struggle through that and ask me for help throughout the project. And so I'm always happy to help. I'm especially with projects. I love doing projects because I think it's a lot more fun than exams. And so I'm always willing to help you through these projects, and kind of work you through the pain points, and kind of help you out where I can. But I need time to do it. Okay. And so I can't help. There's not so much I can do when it's 30 minutes before the project is due, right? And you're only about halfway through the project. And so for these projects and for the activities, start early. Get through your pain points, ask me for questions, and do that as soon as possible, so that we have enough time to kind of work through them. Yeah. All right, a couple questions in the chat. And so will we use MATLAB? No, there will be no MATLAB in this course. So it's just strictly going to be ANSYS. Yeah. Will there be curve grading? And so I don't do curving, because I think it's kind of unfair, but I do adjustments, but I do the adjustments kind of more on an individual basis. Yeah. Question. So will the next class be in person? I'm hoping the next class will be in person, but I'm not sure when I'm going to get back from my COVID test, and so I'm hoping to get the results back before Wednesday. But if I do test positive, then we will be virtual again, and so I'll be sending an email with instructions based on that later on. Yeah. All right. Question. So will we be required to model our own parts before transferring into ANSYS? Most of the time, no. And so most of the times I'm going to give you the CAD geometry that you're going to be working with. But depending on the nature of the projects, I might be asking you guys to do some solid modeling too. And in fact, yeah, actually for the projects, there will be some kind of modeling that's required, but it's not going to be completely from scratch. And so I'm probably going to give you a starting CAD geometry, and you're going to have to modify it for the projects. Yeah. But this class is focused just on the finite elements. And so, we're not going to be focusing on the CADing at all. Yeah. Mm-hmm. All right. All right, textbooks. So the textbooks not required, because I firmly believe that textbook companies are run by the mafia, and they only exist just to rip poor students off, right? And so I'm never going to require a textbook for my courses. But if you do want to pick up the textbook for this class, then this textbook's really good. And so I picked this up. I picked this one up at the beginning of summer. And I learned a lot about ANSYS, and it's really nice because it has a lot of pictures and a lot of examples here. So if you're going to pick up a textbook, this is one of the ones that are higher on my list of recommendations. And so it's definitely a good textbook to pick up for this one. But it's not required. And so, I'm going to be posting all the lecture notes and all the assignments. And so you don't have to buy anything. But if you do want to pick this up, it is a good one. Right? And if you can find a cheap one, or if you can find an even cheaper one on the high seas and with Captain Jack Sparrow, then that's another great option too. So definitely a good textbook to pick up, but don't pay full price for it. Yeah. All right, questions. So waitlisted students. Yeah, so that's a good question. So I know there's quite a few students on the wait list right now, and so I didn't plan on adding that many students from the wait list, partly because of COVID stuff, because I don't want to have too many students in the classroom, but also partially just because I'm usually really generous with adding students from the wait list. But last semester it just kind of really overwhelmed me with the volume of students, and so I'll try to be accommodating, and so I'll see what the wait list is like next week. And so if it's only 2 or 3 students, I'll add you. But if it's like 5 or 6 or 7, then I'll probably only add the first 2 or 3 people. Yeah. But let's wait until next week, because usually first week people are usually shopping around a little bit, and so usually the enrollment kind of settles down by next week, and so we'll talk about it from there. Yeah. All right, course website. And so our course website is going to be on Canvas. And so, probably a lot of you guys have seen this already. And so basically any content that I create for the class, whether it be an assignment, a study guide, lecture notes, tutorials, stuff like that, I'm putting it all on Canvas. And so, you can be sure that, anything I create for the class will be available to you. Okay. And actually the recording for this lecture will be on Canvas as well too. Okay. And so another thing I've created is a Discord server. And so Discord is something that I started, through the pandemic. But even though, and I did it to kind of mimic kind of the in-person experience. So I kind of created it as kind of a space for you to interact with your classmates. But, now that we're in person, you can say that we don't really need it. But I think there was a lot of really cool things that happened on the Discord, right? One thing that happened a lot last year is what you'll notice on the Discord server, there's a memes channel. And so, a lot of students made memes of me last semester, and I loved it. And so, make those memes, share them. I share them with all my friends and family, and they think it's hilarious too. And so, have fun with it. Okay. So, but I think it's a great place to kind of ask questions, especially in this class where we're going to be working a lot with software. People are, you're going to have trouble, you're going to run into errors, and you're going to run into some issues with the software. And a lot of times it's a lot faster to kind of ask the Discord, for help rather than kind of waiting for my response. Okay. So definitely use that. Okay. But I do kind of have to put up a little bit of a barrier. And so last semester, I kind of was really open with students kind of direct messaging me on Discord, but it kind of got a little bit out of control. And so I'm going to say that you can direct message me on Discord, but please only save this for emergencies. And so, what happened a lot last semester was that, I had students kind of asking me for help on projects late into the night, or, while I was out with my fiance and stuff like that. And so it kind of got a little bit out of hand. And so, I would say that if you want to use Discord, I would say if you have a question on an assignment, please use the Discord server and use the questions channel, and so that everyone else can see it and everyone else can answer it if they can. Because a lot of times I was having students directly message me on Discord, and it was the exact same issue, but just times 20, because I had 20 students messaging me about the same thing, right? And so if you put it on the Discord server, then everyone can see it and everyone can benefit on it, and it kind of cuts down on my spam, okay? But if it's a private matter where it's something you don't want to share with the rest of the class, you can email me. So please try that first before direct messaging me, unless it's an emergency, okay? Okay, so any questions on this so far? Okay. All right, so we're almost a little bit out of time, and so I'm going to kind of speed run the rest of this. So course policies, and so I do accept late homeworks, and so if you don't make the initial deadline, you can turn it in late. But I do have to dock 10% off, each day that it's late. Okay, and so I do this again to be flexible, because I know it's deadlines can be really difficult, especially when you have a lot of other things going on. But we have to kind of keep up the pace, right? All right. Regrades. And so I make mistakes on grading stuff all the time, and so if you find that I made a mistake on grading stuff, please let me know, but please try to do this relatively soon so that we're not looking at stuff from week 1 at the very end of the semester, okay? And if you do send me an email, I am teaching 4 different classes this semester, so it kind of gets to be a lot. And so please include the course number in the title or the subject of the email, so that I know exactly kind of what you're talking about. Especially, I know some of you are in multiple of my classes, and so it kind of really helps me sort out my emails and respond to you more directly. Okay. Graduate credit. Okay, and so this is a big one. And so I know that there's another finite element class going on this semester. I know because I'm teaching it, right? And so if you're a graduate student, I would actually highly recommend that you just enroll in this one instead of 410, right? I say instead there, but I would, but what I don't want is I don't want you to enroll in both, okay? Because I've kind of retooled 410 a little bit to be a little bit more similar to this one. And so if you take both classes, it's going to be a lot of the same content, except this one's going to be a little bit more advanced because it's a graduate level, okay? And so the only thing that I really, so you can choose whether you feel more comfortable with 410 or with 540. The only thing I ask that you please just don't enroll in both 410 and 540, because you're almost going to be taking the same class twice. And so I would say about 65% of the content is going to be the same. And so, I feel like that's kind of a waste of, that's kind of a waste of time and a kind of a waste of money for you to kind of experience the same class twice. And so if you're enrolled in 410 this semester, consider dropping that one and just taking this one. Yeah. All right, academic dishonesty. And so, I'll just do this briefly. I don't anticipate this to be a big issue with this class because it's, we don't have any exams, but, please do your own work, right? At the end of the day, my goal for these classes is to have you come out and learn something from these, right? I don't think it's my job to really take, to judge you guys or to say, who's good or who's not, right? I don't really see myself as a gatekeeper. I see myself as, someone that's here to kind of give you useful skills that you can use in the workplace, right? And if you're cheating and if you're not doing your own work, then, end of the day, you're not learning, right? And that's a failure on my part as an instructor, right? And so if you ever, and so I always say this, that if you ever feel like you're struggling in the class, whether just because of time constraints or the material is really confusing you, please reach out to me first, before you resort to cheating or copying from someone, right? I really believe that it's my job here to help you guys and support you guys as much as humanly possible, right? And I want that opportunity to to help you before you resort to cheating, okay? Because if you do cheat, then you're not taking something useful from this class, and that's a failure on my part, right? So I know that not everything in this class is going to be easy, but it's also not my place to judge you or to criticize you, if you ever are struggling. So please never be shy to come to me if you're struggling with something. And I promise you, I'm not going to judge you. I'm not going to criticize you. I'm just going to say, what can we do to get you back on track? What can we do to help you out, with this class? Because, I want everyone to succeed. I finite elements and ANSYS is something that I think is super cool. I think it's really, a really cool, really useful thing. And I want everyone to feel confident out of this class that they can use ANSYS, they can use finite elements really, really well. Yeah. All right, question. So if you took 410 in a previous semester, don't worry about it. I've changed things up quite a bit since then. So yeah, so no worries. The only thing I'm worried about is if you're taking 410 this semester together with 540, because yeah, because then they're going to be pretty similar. But 410, if you took 410 previously, then don't worry about it. Yeah, I know there's several of you, so don't worry about too much. Okay, so we've come to the last slide, and so we're a little bit over time. And so the first homework assignment that I want you guys to do is just to send me an email just to introduce yourself, okay? And you get full credit just for doing it, right? And so everyone starts off with an A. I think that's kind of a nice thing to do, right? And so, I always do this, even if you've had me for, 3 or 4 different classes before, please send me an email, because I really like to get to know, what students are in my class and what you're looking to get out of this, right? Because I think what's not emphasized enough in these kinds of classes that, these classes, you're paying good money for, right? And so I think the classes should work for you. I think you should be able to get out of these classes what you need or what you want, right? And these emails are kind of my way of kind of sussing out, what do you want to get out of this class? What do you want to do with your education, right? And I take that information and I use it to adjust the class. And so I make modifications to my classes all the time based on, what you guys want to get out of it, right? I think especially for you graduate students, I think you guys have a much better understanding of, what you're coming to school for, right? What skills you want to learn here, that you can take back to your workplace or to take to a new job, right? And so I want to learn about those things. So please, please email me, please let me know, and I'll do my best to kind of, modify the class so that it meets those needs. Okay. And so if you can send me your email before Friday midnight, that would be great. And that's another typo in these lecture notes. I did too much copy paste. Make sure you put EGME 540 in the subject line, so I know that you're in this class. Okay. All right, and so that's it for the class. And so I apologize. I know I went a little bit over time, and I know I had to kind of switch to a virtual modality, kind of very quickly on the fly. But hopefully, we'll be back in the classroom soon, and I'll keep you guys updated. So have a great evening, everyone. I'll stick around if you guys have any more questions, and I will see you guys on Wednesday.
Thank you, Professor.
Thanks, guys.
Thank you, Professor. Have a good day.
Thank
Thank
you.
you,
Thank you,
Professor.
Professor.
Thanks, guys.
Thank you, Professor.
Thanks, Michael. Yep.
Thank you, Professor.
Thanks, Professor.
Thanks, guys. Thanks. Have a great night.